Thank you, Mal. So I was in this workshop last year as well, and it's really interesting and fascinating, area, and really like to talk to you and get your feedback on the kind of work that we are doing. Um, so I'm going to talk about two major studies that we have done, mostly focusing on multimodal sensors and geared towards dementia care, improving quality of life, and helping the staff that are taking care of these patients in a nursing home kind of setting. So, okay, so everybody in this group knows about dementia, so I'm not going to talk too much about that. But one of the uh, effects of side effects, I would say, of dementia is that these patients a lot of the times exhibit these behavioral and psychological symptoms of dementia that could include agitation, aggression, resistance to care, and so on. And these patients, they can harm themselves when they get agitated or aggressive. They can hurt or harm other patients or the nursing staff. Now, from a clinical perspective, they would want to know, clinicians would want to know when a person is getting agitated so that preventive measures can be taken. The traditional method is about, manually observing these patients and then do clinical assessments and use scales like PAS, Pittsburgh Agitation Scale, or NPI, and other types of clinical instruments, and literally note them down on a piece of paper. It builds the history. It can tell if a person is agitated over a period of time, but it does not uh, you know it these type of instruments are incapable of detecting or predicting agitated behaviors. Also, these are time consuming, prone to errors. They may have biases, different types of biases, recall bias and stuff like that. So with this issue in mind, we actually wanted to develop a multimodal sensor system so that we can detect and, if possible, predict the onset of agitated behavior. So we ran this study, and I think last year I talked a little bit about some of the results. So if we have some members in the audience from last year, they may see some of the slides that I already talked, but we have some new and interesting results going on. So I'm really excited to talk about that. So in brief, we actually ran this study from 2017 to 2019, where we installed 15 cameras in the common areas of a specialized dementia unit at Toronto Rehab in Canada. And we also installed, and these patients were this Empatica E4 wearable device, which is a multimodal wearable device. It can measure acceleration, PPG, skin temperature, and skin conductance. We also use other sensors, ambient sensors, but I'm not going to talk about that because the data there was noisy, and in the end, we end up discarding them. But this data was also collected. We created a very comprehensive, protocol. We trained the nurses, and as you know, that these nurses, after their 8-hour shift, uh, they write these reports. So we train them in a way so that they can highlight if an incident, agitation, or any behavior of risk kind of incident happens. What was the start time? What was the end time? Location, and other kind of information. And we also have access to the corresponding PAS clinical score, which is the traditional way of noting their agitated behaviors. And then there was another layer of reviewing to improve the quality of these labels, that the researchers, there was another team of researchers that would view those videos, and then basically make sure that the events are marked correctly, and they can further fine tune the start and end times, because it is important to train these machine learning algorithms on correct labels. This is the general information on the data that we collected. The study ran for 2 years. Around 600 days worth of data was collected. From 20 patients, 3 patients did not show any agitation. So the results you will see is for 17 patients, mean age around 80, 12 females, and 411 agitation events were reported, and out of which 305 were fully labeled. Fully labeled means they have start and end time. Some of the events did not have end time. Some of the events may not have start time. And part of the reason is that these cameras were not placed in the private rooms, in the toilets, bathrooms, only in the common areas. So if a person, if the agitation event started, but let's say if the person ends up in the room or something like that, we would not have any information. So there were more than 100 events that did not have the full start or end labels. Now, to motivate the use of multimodal sensors, this is an actual agitation event from a patient. When we think of agitation, most likely like a motor agitation, there can be different types of agitation. Motor agitation is when the person is visibly moving their hands or body parts, right? So then the accelerometer can pick it up. But then I can tell you many examples where there was a patient who was restrained to the chair, right? And they were not moving, but they were very, very agitated. So in that case, accelerometer will not work, and perhaps we can get more information from their skin conductance or their heart rate may increase. So in this example, sorry, the labels on the y-axis are very small. So so blood volume pulse first, first graph. The second is accelerometer. Third is heart rate, and fourth is temperature. So even though we see a little bit movement in the accelerometer, but then accelerometer also shows movement at other places. So only accelerometer is not the only modality good for that. And we also verified this with our experimentation, and I'll show you. So that is why perhaps we need more than one type of sensor to study this type of complex behavior. This is the machine learning pipeline. This is all published work, so you can read into that. So basically, we did some signal processing, filtering, feature extraction, and then we did multiple classifiers. I'm going to show you the results of the best classifiers, but we tried multiple classifiers and multiple techniques we tried. So this is the result of that study, and we can see. So we tried on a single sensors, and we also tried their combination. And what we learned is that combining different sensors gave us a pretty decent, I would say, AUC ROC value of 0.82. This paper, like as I said, is already published. And since publication of this paper, we have further made some further improvements, and now we're getting a even more sorry, AUC ROC of around 0.9. So I think this result was very interesting and exciting at the same time. It was one of the first study that looked into the agitation behavior from a multimodal wearable sensor device. Around 25% of our patients had problem in wearing the device, but otherwise, the study went quite smoothly, which was also an achievement, I would say. Another view of the results. Now, we also collected huge amounts of data, and it ran into terabytes of data. Just imagine these cameras were collecting 16 hours of data. We were not collecting it in the night. So automatically, so we set up a system where automatically these video cameras were switched off in the night. So we were collecting 16 hours of data per day for these many days. So we ended up having, 30 terabytes of data. So that was a large amount of data. But what we did was, for now, we started with one person, around 35 hours of data, 25 hours of training data, and then around 11 hours for testing and 24 hours for training. Now, one of the things that we observed was, and in the multimodal sensor also, even though we tried it as a supervised classification problem, even though these patients are highly agitated, that's why they come to the specialized dementia unit, because they are diagnosed with high agitation and aggression kind of behavior, but still they are not agitated all the time. So if you're looking from a day's perspective, the number of agitation events or the duration in comparison to the normal activities was not high. So what I'm trying to say is that there was a huge skew in the data. Now, in the videos, it is really hard to also label that kind of behavior. Like, even though we had labels, but when we realized, like, in the sensor data, we had around 3% agitation, and 97% of the data was normal because they were normal most of the time, right? So for the video analysis, we actually took a different approach, and we tried to detect agitation as an anomaly. So we tried to build our classifiers on only the normal activities. So we trained the classifier on these 24 hours of data, and then we labeled the testing data with normal and agitation, and then we see, can this classifier detect this agitation as an anomaly. So this is a 3D autoencoder kind of approach that we took. We also tried different variants of this. In another variant, which I'm going to show you some results, some of the convolution layers were replaced with 2D convolution layers. So different architectures we tried, but this was the base kind of idea, the baseline idea. I'm going to show you this video. So this is an actual video, and you will see a patient coming to another resident, and they're going to kick literally and then walk away. We never showed this video to the classifier. The classifier is only trained on the normal data, and this is a test video that we showed. So let's quickly forward. So you see this patient is now entering. At the bottom, you see this this graph. This is actually the reconstruction error of this autoencoder, and the idea is that if it is close to normal activity, then the reconstruction error will remain lower. But if something anomalous happens, then the reconstruction error will go high. So you see here at this point, the person kicked the resident and then walked away. Now, this happened for a fraction of a second, if you see, and the staff is not there all the time. Nursing homes and LTCs have an understaffing problem. Even though we have staff, they cannot be there all the time. Even though they have CCTV cameras installed in these nursing facilities, but those nobody's watching those cameras all the time, right? So this minor incident happened, and then the person walked away. But we were able to pick this up, and this was a fascinating and very exciting result for us, and very, very encouraging for the type of work that we're doing. So we have published this work recently this year. So if somebody's interested, then they can look into the paper. But then what we also did was there were still concerns because we were working with video. So there were concerns that, the patients and the residents and other people walking in the unit may be identified. So we also looked at it from a privacy perspective angle. And the results that I'm going to show you, these are like brand new results. And we are actually writing a paper around it. So it has not been published yet, but these are very brand new results. So one of the first approach we did was trying to do like a body pose analysis, body joints analysis. So you see these sticky man kind of image. So again, the same person, black background, this person is like coming, and and as you can see, the body pose is not very stable because these cameras are like real camera feeds. The cameras are far away. So you see the person is coming near to the other resident, and then they will have a slight interaction, and then they walk away. But these body joints were not very stable. And then you see the person is walking away. Now I'm going to play the other video. In this video, there is the first one was open pose. This is another body pose, which is the detectron. So this is also fairly unstable, but we overlaid this over the video to see if this works or not. So it is. So you see, again, it is kind of working. But one of the criticism of this approach is like these body joints were kind of unstable. Now, the third approach that we call as the segmentation approach. In this approach, what we do is we literally blacken this entire person. And here you don't see any revealing information, but then you see the person kicked and is walking away. And this actually approach not only is privacy protecting, so you can see the person still, but you will not make out anything. And then so using some in-painting technique, and then this third approach actually gave us the best results. So I'm going to show you the new numbers. Oops. So we tried two types of convolution autoencoder approaches, and using the raw video. So we were able to get, using this segmentation mask approach, approximately very similar results to using a raw video, which is again very encouraging that we do not, and we had this feeling that we don't need to see a person's face to understand if they're agitated or not, because this is a very physical kind of activity, right? And we were successful in just using their segmentation mask, and we got AUC-ROC, which is actually very, very similar to using a raw video. So this builds the case that we can detect these agitated events in a privacy protecting manner as well. Now, there are many work surrounding this idea, and we are very, very excited and full of ideas around solving other related problems. So I already talked about the privacy protecting modalities, and we are continuing to extend this work for other patients having data from other cameras. So we have lots of data so that we can explore. The other part that you might be also thinking and saying that, okay, you did the agitation, that is great, but what about if we can predict these behaviors? And this is a very hard question to answer, but we have started working with one student and trying to see if we can get some markers before the actual agitation events happen. We have another paper that I did not talk, where we actually showed that these behaviors are highly personalized, right? The results that I showed was for the generalized population, but in personalized models, we see that for some people, these the performance goes very high. For some people, unfortunately, it is not. So it's a very personalized, specific behavior. So in those situations, can we predict? Because if we can even predict a few seconds before, then I think it can prevent a lot of those accidents that can happen. The second direction that we're looking at is the unlabeled agitation data. Like, as I said, all the events are not fully labeled. Can we leverage that information? Can we leverage the rest of the data which is not properly labeled? And can we build classifiers around it? And for computer science folks out there in the audience, we have formulated this problem as a positive unlabeled classification problem, or positive unlabeled learning problem. And we are currently experimenting, and I hope next time we'll have some interesting results to share with you on that. So these are the two directions. Now I'm going to change gear at this point, and I'm going to talk about another very exciting study that we are currently doing, and it's called the STIX study, which is actually closely related to real-time location systems. So if you guys know about the RTLS systems, basically these are indoor positioning system that can give you the X, Y, Z, whatever coordinates of a person moving in an enclosed space. It's very similar to GPS in the house, like the way GPS works outside your house. So it's something like that. So basically you install these beacons, and you have these IR sensors that you can wear like a watch or something like that. It can come in different shapes and sizes, and it can, traditionally they were used for in factories and warehouses, even in hospitals, for asset tracking objects, if the objects are lost, things like that. So and transportation where they move large amount of objects, so they wanted to track if they do not lose any of the objects, right? But now but we also know that it can give us very vital, rich spatiotemporal information about the walking patterns of a person, or the path that they're walking. So the application that we are currently using it is for characterizing the severity of cognitive impairment in dementia and its progression over time. So the clinical premise was that we know from literature that wandering behaviors are associated with dementia. So whereas people with no cognitive impairment would walk in a more, I would say, standardized manner, but people with dementia may exhibit these wandering and erratic, paths over a period of time, and depending upon the degree of cognitive impairment. So the intuition, when we looked into this data, the intuition was that the dementia behaviors can be visually discern and distinguish based on the walking patterns, as the literature suggested. So we get we use this data, which is called the USF data set, which was provided to us by Dr. Bill Kearns from University of Southern Florida. That's what USF stand for, and they had this data for collected over one year from 10 people. One person has no cognitive impairment, and then the rest of them had severe or mild moderate cognitive impairment, and it gave XYZ coordinates for each of the participants. And they installed these these sensors in a room, and the patients in one common area, and the patients can enter and leave uh, at any given point in time. So the problem was that because the patients can come and go at any time they want, we had lots and lots of missing data. So it was not these sensors were not placed in the entire facility, but only in one common area, right? So we can only see their paths when they're in that area. When they're outside the area, we did not know. So that gave us a lot of missing values. So this is an example image of the first image is about of a person with no cognitive impairment. Second is mild, moderate, and the third is a severe cognitive impairment case, collected over a window, what we call as the window of 30 minutes, right? So as you can see that the person is with more severe cognitive impairment, their paths are more all over the place. So this is kind of a visual intuition that I was talking about. So by looking at these, we came up with this research question: that can images of walking paths identify the degree of cognitive impairment or not? So based on to do that, the next step were pretty simple. We designed a very simple convolution neural network architecture, and basically a 3-class classifiers for no cognitive impairment, mild, moderate, and severe. And we did a lot of experimentation, which are the details are outside. I'm not going to talk right now, and this paper is also currently under review. And we also tried traditional machine learning algorithms like support vector machines and random forests and stuff like that. We extracted features also like fractal dimension and other types of standard features from that data, but we also considered it as an image. And our approach significantly outperformed the traditional machine learning methods, and we got around 87-88% accuracy for a 30-minute window. And like as I said, that because the persons were not there in the room all the time, so there was lots and lots of missing data, and we did an experimentation with that, and we found that we can still get very high accuracy with even with a lot of missing data present in these paths images, which was also encouraging, which kind of shows that you don't need data all the time. Even if you have 70-80% of the data, that should be fine. So this paper is currently under review. And we also compared our model with some other standard deep learning models. So our model is that the last, and these are some of the standard models, both pre-trained and not pre-trained, like trained from the scratch. And as you can see that with our simple 2-layer, 3-layer CNN model, we were able to achieve very similar performance to, for example, ResNet 152, and which has more parameters in comparison to our model. So, I mean, complex models are always not really helpful, and simple models are also easy to explain. And due to the time, constraint, I'm not talking another important aspect we did. We actually did the interpretation of these results, and we used the GradCam feature. We actually adapted this algorithm for our case, and we came up with a new metric, what we call as a cognitive impairment severity value. And we were able to show that the CISV value that we obtained from a simple CNN can be used like as a threshold to classify these patients, just one value. I mean, not 100%, but to a larger extent. And with ResNet and other complex models, we were not able to get those kind of thresholds, or the features were not very interpretable. So simpler idea worked in this case. Now, in the remaining part of my discussion, I'm going to talk about this STIX study, which actually stand for space-time index development for health problems, especially related to dementia care. And this is an study that is ongoing right now at the specialized dementia unit, which is actually a 20-bed, 15 to 18 patients it can have. And normally they have acute BPSD or patients. And unfortunately, due to the COVID-19, I mean, the study was supposed to start early last year or before that, but there was a delay, and we only started data collection from last October. So far, we have collected data from I think 9 patients. So I want to show you this video. So this is the actual layout of the dementia unit with all the rooms and common areas and all that. And this is an actual data of a patient walking in the unit. So you can see that they are in their room, and I'm going to fast forward it. So at the beginning, they are in the room, still in the room, and then they started moving around. And here it's actually fast forwarded, so they're not walking at this speed, but just for demo purposes. And now you see they started walking, and then they started walking all over the unit. And if by the end of the video, they have covered all the major areas in the unit. But some areas are dense, so they're spending more time at some places and just walking around at different places. So basically, this data is also very similar to the USF data that I showed you, but the difference is that we have data for almost all the corners in the unit. So we are actually collaborating with a Canadian company, Tenera Care, who have developed, it's from Nova Scotia. They've developed this wearable device, and we place these beacons to collect the data, and it transmits XYZ coordinates of the patients at 1 hertz. And so we also collect the PAS score after every shift. And so far, we have collected data from 9 patients, and for other patients, the data is ongoing. Now, in this data set, because this is a fairly recent data data is being collected, so we do not have definitive results for this now. My student just recently did some preliminary work on that, so I'm just gonna show a very sneak, peek, kind of preview, and these results will change over a period of time. But for now, we are, like as I said, we just do not apply deep learning because everybody does that. We also, from a clinical perspective, we also try to understand the features that can be extracted, and if simpler models can be built. So the first approach is always looking for simpler models, like we did with the USF data. Our knowledge about the features have also improved over the last year. In the USF data, we only had, I think, around 16 or 20 features. Now we are able to extract 43 relevant features related to many different aspects. So, for example, total time spent in each room, personal rooms, common rooms, fractal dimensions. These are other standard features that have been used in the past. Speed features around speed, how much time they are, stationary, and time spent at the exit doors and things like that. So we are trying to understand the data. We are trying to understand the behaviors. We get feedback from our clinicians in our team, and based on that, we're extracting these features. So far, 43 features have been extracted, and these are the very, very preliminary results. The AUC is not so great so far. It's 0.6, but we are hoping that with improvements on the signal processing side, there were some sensor calibration issues. So the data, we are still working on calibrating the data and all. But these numbers can actually give us a little bit of idea about what is going on. Now, agitation, as you can see, is a motor kind of behavior, right? And motor behavior is like when a person is kicking, punching. I mean, there are different types of agitation, but So these RTLS data is good in detecting the paths and everything, but it does not have an accelerometer kind of thing, right? So we will have to see how good this can be used for detecting the agitation behavior, right? Um, so just the path information, can it provide us clues about that? So we are looking forward for the results and also trying to use our previously developed deep learning model and see if it can be adapted for this problem. However, the other problem that we are more interested in is the social engagement. So this is again a layout of the same dementia unit, and this actually shows the proximity between two patients, A and B. Social engagement within a dementia within a unit between the patients is also important to understand, to kind of figure out if this is causing any distress to them. Are they okay with it, or or does it lead to agitation or other type of risky behavior? So this is just a very simple diagram of proximity analysis between two patients. So over a shift, so you can see that these two people, A and B, are together sometimes, and then a lot of the times they are far away from each other. So if we can analyze their behavior over a period of time, two people or multiple people, then maybe we can get some inference about the overall social engagement that is happening in the unit. Uh, and most of the time, we have no idea about what is going on in the unit. So this is it. And I would like to thank our sponsors, Schroeder, AGEWELL, and Alzheimer Association for funding these, research. And yeah, so I'll stop now. And I think the next speaker may be waiting already. Right. And I'll be back, Ma, in 30 minutes. And hopefully, if there is any Q&A, then I'll be happy to address that. Thank you.
Thank you, Shehroz. Thank you.